So I've had a cup of coffee and a nice cake, fresh cake, and now I'm on the second cup of coffee. While doing that, I browsed the section, and there wasn't much information except this theorem, this proposition. And I hope if you don't have the book that you get a clear picture of it. So if you stop the video, you may be lucky. So, and it appeared to me that we might be able to use that. So that's what we'll try now. So a new page. There we go. So we have that 1 is a congruent number, and then there is x, which is a square of a rational number, so that x plus 1 and x minus 1 are squares of rational numbers as well. Alpha, beta, gamma being rational. That was ugly. Now, now let's see what we do. Do we multiply them? Or do we add? How about, well, we need to get fourth powers, really. Adding them 2x, that gives all these powers of 2, that doesn't matter, I don't like very much. How about squaring them and subtracting them? Let's try that. And then subtract them. And then x is the square of a rational number. Now what do you say? Wasn't that what we should prove, really, or was it? Show would have integer solutions. So we have to multiply by the some common denominator here. So now how do I do that? I should have written them as with some common denominator. And then we put it into here. And then we multiply by n to the fourth. Voila! Finally. So that means that if I had to work it out from scratch, then I would have to repeat the proof of proposition 1. And I'll tell you, when I read it, felt quite alien to me. Well, I'll have to read it once more to get it nice. So that was part A. Then that equation has an integer solution. Lovely. The next one is to prove that that doesn't exist. So we have to prove that x minus h4 equals u squared. Why should it be then? Has no intersolutions. Of course, except 0.0.0. It looks as if we should try the old trick of factorizing the two sides. I believe we can assume that the 3 has no common factors, and therefore 2 of them can't have. So I think we're the same way. Of course, this is still the problem with 2, but except for 2, if a prime divides u, then either its square divides this or this. So let's assume 2 divides u, and those two. Then it divides 2x squared and 2u squared. Oh, let's take it very easy. If 2 divides u, then 4 divides u squared. Ah, now that's a good idea. We could probably have done that with the first exercise as well. Then 4 divides this, and that means 2 divides x and u and y, of course. That's impossible. So that means that this is square and is a square. Do we have any examples of this? Well, actually, we have to prove we can't find an example. Think of a non-mathematician watching this. He'd be bored to death. You know that a lot should be going on in my head. Actually, I'm still not very creative when the video's on, so not all that should is going on. But let's just keep it on for a while to see if I get any ideas online. And I'm not even online, it's just a video capturing what I'm not doing. Oh, I just say there's something about with you being art. I didn't show that, did I? Is it clear that you is art here? So could X and Y both be art? B and G both be art? Since we end up with, oh, it's you being art. On the contrary, my U is even. Well, let's assume that U is even. I don't know what I'm doing here. That's better. Oh, then 2 must divide u. But then 2 divide them all. Well, it can't exist with 2 even. That's obviously impossible. So why did I end up with 2 being even? So we squared them, got this. And then we were home, but unfortunately u is even. And that is obviously impossible. Or is it? Hmm. Well, here it is. So now if 2 is even, then 4 divides this. And I agree this is impossible. We'll just have to do this to activate it. I don't know why. So that was another dead end. If u is even, then it's obviously impossible to solve the equation, but then it's unrelated at all to Fermat's last theorem with n equals 4. I think the book is right, and I have made a mistake, but I'll have to go through everything again. I'll do that without recording and then report on where the error is. So that stops it here.